multiple choice questions. Question 1. Which reaction has an enthalpy change equal to the standard enthalpy of formation of potassium oxide? Can't be C. It can't be A. It can't be A because the definition of standard enthalpy of formation is the idea it's a 1 mole of compound is formed from its constituent element. Is that 1 mole? No, that's 2. So it can't be A. It can't be C because it's got positive charge or a negative charge. That's ions. We're not working with ions, we're working with elements in the standard states. So that the B or D. Well, B, it should be O2 or half O2, and therefore the answer is D, because B is wrong. Question 2. What is the enthalpy change in kilojoules per mole to power mass from this reaction? You can see I've done a bit for it. I was struggling with it. What we need to do though is manipulate the reactions. So how would we do that? Well, if we do this first reaction times by 2, what will we get? We'll get 2Fe solid plus a half times by 2. So it's just going to be O2 gas arrow 2FeO solid. And we've also got 2Fe solid plus 3/2 O2 gas arrow Fe2O3 solid. And what will happen is all we have to do is, because what we've done now is we've got the doubled reaction 1 so all we need to do is times that by 2 and do the second one, subtract the first one. If we do that, we'll get this reaction and therefore we'll get the enthalpy change for this reaction. So that times by 2, so it's going to be minus 822 minus 272 times by 2 minus 822 minus 272 times by 2 minus 278 kilojoules per mole to power minus 1. Don't have to worry about the units because they're both in kilojoules per mole to power minus 1, and we're trying to find it in kilojoules per mole to power minus 1, the enthalpy change. Question 3. Some enthalpy change data are shown. What is the enthalpy change in kilojoules per mole to power minus 1 for the following reaction? Solve this question. We're going to have to use enthalpy changes, obviously, to calculate enthalpy change for this reaction. What we're going to have to do, though, is what we can do is reverse reaction 1. So for reaction 1, that becomes CH4 gas arrow C solid plus 2H2 gas. And therefore, because we reversed it, we reversed the delta H, so therefore it's going to be positive 75. Now we've done that, we need to modify reaction 2. We clearly want 4 H's here. We've only got 2 H's here, so we need to times reaction 2 by 2. So we need to times this by 2 as well. So what will happen is we'll get CH4 gaseous arrow C solid plus 2H2 gaseous. And we'll also have 2H2 gaseous arrow 4H gaseous. And what will happen is all we have to do now is add them together. 2H2s will cancel out and we'll be left with CH4 in its gaseous state arrow C solid plus 4H in its gaseous state. Perfect. And that will give us the enthalpy change for this following reaction. Now how do we do that? How do we do that? Well, firstly we reverse reaction 1 and we double the reaction 2. So all we have to do now, 436 times by 2, 436 times by 2, because we doubled reaction 2, minus 75, because we reversed reaction 1, so the enthalpy change became reversed. Instead of negative 75, it became positive 75. 436 times by 2, minus 75. Sorry. Because we've added them together now, all we have to do now is, instead of, because that's positive, and we're trying to find an enthalpy change of this, is actually going to be 75 plus 436 times by 2. Not that. 75 plus 436 times by 2. 947 positive kilojoules per mole to power minus 1. They're both in the correct units, and we're trying to get in kilojoules per mole to power minus 1, so we don't need to worry about converting the units. Question 4. What is the temperature rise, delta T, in Kelvin when 504 joules of heat energy absorbed by this much mass of solid iron? Specific heat capacity is that. Okay, now first thing I would like to do is write down the equations. What could I possibly need for this? Temperature rise. Temperature rise. Q equals mc delta T. Possibly need that. And we're trying to find temperature rise, so delta T. Delta T equals Q divided by mc. Q, I don't know Q. Temperature rise, I'm trying to find temperature rise. The mass of solid iron, I've got that. Specific heat capacity, I've got that. But I've got temperature rise when... No, perfect. I have got Q. 504 joules of heat energy are absorbed. So I do actually have Q. So all I have to do now is delta T, temperature rise, equals 504 joules divided by the mass in grams times by 1000, 1, 2, 3, 110 grams. Yep. 110 times by 0.448. .504 divided by 110 times by 0.448. That will give me 10.2. So then B, right? Absolutely, it's going to be B then. Now let's mark it. Question 1D, question 2B, question 3D, question 4B. Yeah, it did look like I was going to have to maybe use a lot of formulas, but in reality, use this formula, rearrange it, substitute the values in, and you got your answer. And obviously you do need it in the correct units. 504 Q is measured in joules, so we need that in joules. Obviously the mass we want in grams, so times by 1000, and specific heat capacity of iron is also in grams, and that's fine. And that will give us the temperature rise in Kelvin. 1.02 times by 10 to the power minus 1, aka 10.2. And that's the end of the multiple choice question.